Morning, good afternoon, or good evening, depending where you are located. I'm going to present a talk entitled Optimization for Renewable Energy Planning. I'm Dominic from University of Nottingham, Malaysia. My talk today covers sustainability and climate change. I'll talk about some optimization techniques that we can use for renewable energy planning. My techniques that I will cover include process integration as well as P-graph. In the first place, let's talk about this sustainable planetary boundary. About a decade ago, some scientists have proposed that the safe boundary for CO₂ carbon dioxide concentration on the atmosphere should be kept within 350 ppm by volume. As a reference point, the pre-industrial value was 280, and as you can see in the last column of the table. At the moment, we talk about 400 over ppm. When the paper was published a decade ago, it was 387. This was a famous Keeling curve, which records the CO₂ concentration in Hawaii. And you can see that it was a couple of years ago when it passed the 400 ppm by volume. This was during 2013. And this chart shows some of the latest concentration of CO₂. I took this last month. The CO₂ concentration on Mother Earth has recorded at about 411 ppm just last month, and the highest was actually recorded in May 2020. Half a year ago, it was 417 ppm. And some of this extreme climate event has been associated with climate change. For instance, the bushfire in Australia started last year until early this year. The California wildfire is still ongoing, I believe. You can see that the Golden Gate Bridge is more or less covered in red color because of the dust. 2015, the United Nations launched this Sustainable Development Goal, SDG. Two of the important goals that I would like to highlight are Goal number 7, affordable and clean energy, as well as Goal 13 on climate action. For Goal 7, the affordable and clean energy, it clearly spells out that renewable energy has to be making progressive gain in the electricity sector, while energy efficiency continues to improve. Goal 13 on climate change. If you visit the United Nations website, you can see that it says this is the second warmest year on record in the last decade. Down there you can see that the Paris Agreement adopted in 2015 aims to strengthen the global response to treat the climate change by keeping a global temperature rise below 2 Celsius by the end of this century. And this is going to be pursuing efforts to limit it to 1.5 Celsius. And this was also in 2015, the same year as the SDG launch. We talk about various technologies in order to combat climate change. Certainly, one technology alone is insufficient, and you can see this, what we call technology wedges, with a range of techniques that we should be using in order to capture CO₂, to reduce them to the baseline. And certainly renewable energy is one of the most important aspects that we should look at. I will show you the first technique that I will talk about, the optimization methods. This is called process integration. This technique was started in 1970s for heat exchanger network synthesis during the first world oil crisis. A decade later, it was extended to cover mass integration, where mass separating agent is to be minimized in order to prevent pollution. Half a decade later, a special case was launched, which is nowadays called water pinch, or in more general term, this is water minimization, where we recycle water in the process plant. Production chain planning was launched in 2002, followed by hydrogen pinch in the same year, and later on we have this property integration that talk about the recycling of solvent. One important establishment was located in 2007, where carbon pinch for energy planning was launched. This was a joint effort between Professor Raymond Tan and myself. Let me just show you how process integration works. For those from chemical engineering background, you probably learned about pinch analysis. This is a very famous tool established to cater heat recovery system. This diagram shows you the composite curve where pinch can help you to identify how much energy can we recover by minimizing hot and cold utilities. With that, you can design a heat exchanger system, what we call the heat exchange network, in order to maximize the recovery of energy. The same tool was also extended to cover mass recovery, which includes water and hydrogen integration, where we plotted some kind of composite curve, sink and source composite curve on impurity versus flow rate diagram that identify the flow rates that we can recycle and trying to minimize the waste generation. You can apply this for water recovery, which you can cut down your fresh water intake as well as wastewater flow rates. And if you apply it for hydrogen, you can cut down the imports of hydrogen in the refinery and reducing the purge streams. And that also means to minimize waste as well as CO2 indirectly. I won't go to the detail. If you are interested on this domain, you can pick up some of these references. These are all the textbooks available for heat and mass recovery systems for process integration. Let me draw your attention for renewable energy planning. This is the special cases that we developed more than a decade ago on something called carbon emission pinch analysis, or in short, CHEPA. The first paper was published in 2007 by myself and Raymond. If you look at the diagram, it shows you four sources. These are the energy sources, which can include fossil fuel as well as renewables, trying to match them to the regions or countries that require energy, which is what we call it sink. We're trying to find the best combination of matching sources and the sink in order to minimize CO2 reduction. Let me show you a simple examples where you have the energy sources in the first column. Emission factors for all these energy sources shown in column 2, and their available sources are also found. We are trying to match the 4 energy sources to the 3 regions. You can see in the last column, which is the emission limits for each of these regions. We need to ensure the moment we pair or we send the energy sources to the region, we should not exceed the emission limits set by all the regions. The total emission limits, if you add up the 3 regions, it should be 100 million tons CO2. Okay, and what we are trying to do is to maximize the usage of fossil fuels, trying to minimize renewables. The reason is that renewable is still a transition energy source, where you have many other considerations such as the intermittency, and it's not as cheap compared to fossil fuels. So what we do, we'll plot a CO2 load versus energy diagram, where we place the 3 different regions in this diagram. You can see that the three segments representing the three regions have ascending slope. That slope actually represents the intensity of this region. If you check again, the slope actually represents the division between the emission limit by the energy consumed of these regions. The steeper the slope just means that the region can tolerate higher amounts of CO2. This could be industrial area, for instance, R3 in this case. Okay, R1 obviously have a lower slope, which means that intensity of CO2 is much lower. Per amount of energy, the CO2 tolerable in this region is much smaller. We can say these are cities with lots of residential. Obviously, some of these cities will require higher amounts of energy, represented by the horizontal distance. Some regions can tolerate higher amounts of CO2, such as the one in R3. But in total, these three regions should not accept CO2 limits that is higher than 100 million tons. Okay, and the total energy it requires is 2 million tetrajoule. We have some fossil fuels with us: natural gas, oil, and coal. Similarly, the slope of these energy sources represent its intensity. The steeper the slope is, it just means that this energy source has higher CO2 per amount of energy. Now you can see that the three energy sources is insufficient to cater the needs of the regions. So what we need to do is to blend in some renewables. So by pushing this line to the right hand side, the opening gap on the left represents the amount of renewables we need to fulfill. In this case, it's 810 thousands tetrajoule of energy. In other words, the moment I blend in this amount of energy, I will be able to keep the CO2 emission below the limit which is given by the blue line. And the extension of the sources, okay, you can see 410,000 tetrajoule of coal is actually on the right hand side beyond the sink composite curve, the blue line. That amount is to be phased off. Okay, even though you can use this total amount of coal, we have 800,000 tetrajoule of 600,000 tetrajoule of coal. We do not need to utilize all of them because 410,000 tetrajoule of energy is to be removed. Okay, they should be phased off because in order to keep the constraints of CO2 emission within these three regions, we need to use 810,000 amounts of renewables. Okay, the blue line always represents the limits that we can tolerate in terms of CO2. We need to ensure the sources that we place, which is represented by the brown composite curve, has to be to the right hand side and below the blue line. The blue line is a limit. You can't have the brown lines crossing the blue line. So by keeping the brown line to the right hand side below this blue line, that basically says that the three regions are accepting energy which is lower than the permissible CO2 loads that they can tolerate. Okay, that is below their limits. That's fine. Now, we have seen these techniques, what we call carbon emission pinch analysis, being applied in different parts of the world. This was a case study reported by some Ireland researcher. Similarly, the technique has been applied in New Zealand. And let me show you a case study that we applied in China. This is Shandong province. There's a small county called Lanxi. Within this county, there are different towns. As you can see in the map, there are altogether 15 towns within the Lanxi county. When we perform the targeting, we know that you can see the two blue lines pointing you the levels for 2012 and 2020. These are two different targeting years where the energy planning was started. It was started in 2012, planning to meet the energy target in 2020. And 2020, if you look at the horizontal distance, the dotted line says that the 2020 CO2 emission is going to be 80% of that reference to 2012 levels. However, you notice that 2020 have a larger horizontal distance. It means that the energy is expanded, so more energy is to be consumed. However, the CO2 has to be reduced. The only way to achieve this is by blending in some renewable energy. For this case, they are trying to match the results by using biomass. Okay. Now, this Swansea County contains a lot of biomass. However, it is not easy to convince the farmers to sell the biomass or in order to collect the biomass from different towns, because for a start, we need a lot of efforts to convince them to sell the biomass over in order to protect the environment. For low-income people, their main business is to get profits in order for their daily activities. So, in the beginning, when we started this analysis by assuming 100% collection efficiency, obviously we can achieve the targeted biomass requirement. Then the local authorities realized that 100% collection efficiency is just too optimistic. They are looking into 80% collection efficiency in 2 years, and this was the resulting situation. If you are going to collect all this biomass in Town 2, given by the left-hand side picture, that is going to be the situation where you will be able to achieve something like 750, still possible. And if it is going down to 40% collection efficiency, which is the immediate implementation, they realize that it is not possible to match what has been targeted up front. We actually need to make adjustment in the calculations in order to reduce the targets for renewable energy. So for a situation, planning between 2012 to 2020, this is an 8 years duration where we can go step by step. So we can obviously start with 40% collection efficiency, then go with 80%, eventually 100% efficiency. That will be a better way of planning for renewable adoptions in order to convince the local people. Another later work that we do recently is something called negative emission technologies. We know that renewable energy is good, okay, especially those from biomass. However, no matter how good it is, biomass will still emit a bit of CO2, even though we say that this CO2 is neutral because the photosynthesis will absorb CO2 from the environment. A better way of adopting climate change abatement is to apply something called negative emission technologies, where we can capture CO2 in the atmosphere and put it underground. One of these more reliable techniques is Biochar. Another one is called biomass energy with carbon capture and storage. It means that we will burn biomass in the power plant, and with that nature, the biomass energy is really carbon neutral. Furthermore, we will install carbon capture and storage facilities to this biomass power plant, and that will capture the CO2 and we will inject it underground. Doing this will actually achieve negative emission entirely. Okay, so CO2 will be captured, at the same time the biomass can be burned into energy, and that actually help you to reduce CO2 for sure. Similar in the earlier the diagram. In this case here, you can see that we have renewables, we have natural gas, oil and coal that trying to fulfill 60 terawatt hour per year of energy. Without NET, without net emission technology, we need to put in 18 terawatt hour per year of renewables. That is fine. However, in some countries this may not be directly applicable because of many issues, such as land. In order to plant the crops, you need a big area of land, you may not have that amount of land. So one of the techniques that we can make use is install CCS technology in the biomass power plant. Okay, if we do the graphical analysis, we can see that, for instance, if you want to cut down the emission further, okay, we put in this demand composite curve, which is actually the vertical distance represent the amount of energy, amount of CO2 that we wish to reduce. At the moment, CO2 is running at 31.2 megaton per year. If you want to cut it down by, let's say, half, doing renewable is no longer as easy because you need a substantial amount of renewable, and you already have running the maximum at the moment. So what we can do is install the CCS technology and in biomass power plant, and by doing so, we can actually use the same amount of renewables, but install with CCS technology that will help you to reduce CO2, okay, up to the required levels. This is a concept which is to be further refined in the future, but for our preliminary work that we did, and is involving an iterative procedure. Okay, if you are interested, you may get this paper from Industrial Engineering, Chemistry and Research. We have just published this a couple of weeks ago. And let me last show you the other techniques called pgraph. This is an optimization software which does not need too much of a computational effort. It is also graphical in nature. It has a good visualization interface. I'm showing you a case study that we did for biohydrogen production from some industrial effluent. In countries like Malaysia, Indonesia, Brazil, Nigeria, there are lots of palm oil plantation and palm oil mills. One of the biggest effluents from this palm oil mill is called the palm oil mill effluent, POMI, and it's a very good source to produce biohydrogen. So what we need to do is to send the biohydrogen to the areas where it requires hydrogen, and doing so will help you to reduce the fresh hydrogen that we have to purchase from fossil fuel sources. But in order to do that, we need to go through the compression substation before we can send it to the hydrogen sink. Okay. Now, using pgraph will help us to identify where the substation is to be located, and this actually take into consideration of geographical situation in the regions that we analyze. Okay, and you can actually select where exactly you wish to put the substation, and the model will help you to determine whether to send the effluents to which particular substation for recompression before it is sent to the sink. Okay, this was a paper published in International Journal of Hydrogen Energy. We're showing a map here. If you're familiar with Malaysia, we have a big island called Borneo, and this is in the northern part of Borneo, where palm oil mill abundance. There are maybe about 300 over palm oil mills where palm oils are converted from fresh fruit bunches into edible oil and some oleochemical downstreams. Now, one of the byproducts from the palm oil mills is called palm oil mill effluent, POMI, which is very rich in its organic content. So it is easy when you can convert it into biohydrogen to be utilized in some plants. Okay, for instance, if you want to send it to refineries or methanol plants, these are processes that will consume hydrogen. However, channeling it from different parts of a state is not as simple. We need to plan ahead in order to have the pipeline channeling the biohydrogen. So one of the good tools to use is pgraph, where it can help you to track which location is best to put a substation and where the biohydrogen can be sent from the mills. You can see that the green dots are the palm oil mills, the yellow dots are the compression substation. We can ask the software to determine whether shall I send the effluents from mill number 1 or 2 to substation 3 or 4. So this can be decided, and that will give you a network as such that cut across the whole region. Eventually, we still have to top up a bit of fresh hydrogen from the fossil fuel, but that is minimized. Okay, it is in the minimum value, right? And this is a very nice waste to energy sort of application where the palm oil mill effluents can be fully utilized, or else it's actually generating CO2 releasing to the environment. And it's actually quite polluting if we just release to the river, because it COD, chemical oxygen demand, is about 30,000 parts per million. It's very, very dirty wastewater, right? So in recent years, lots of mills owners are converting it to biogas, and from biogas we can also convert it to biohydrogen. And this was the application that we have tried with this particular software called pGraph. All right. In view of time, if you are keen to learn more about process integration, welcome to get this new book that I've published together with Raymond. This is on process integration approach. Unfortunately, we didn't have time to include the pGraph, but we foresee that we'll include it in the future for new edition. And the book also contains some application of process integration in China, India, UAE, Malaysia, and Taiwan. It's not a very thick book. It's handy collections for if you are keen to apply the process integration technique into renewable energy planning. Apart from graphical technique that I've shown you in the beginning of the slides, I have also included some optimization method. Right. With that, I would like to thank my collaborators. From the left to the right, we have Raymond Tan from Philippines, Dr. Chia from China, Puru is my new PhD student, and Professor Yu from Korea. If you have any comments, feel free to drop me an email and to talk about collaboration or future extension of some of this renewable energy planning. With that, thank you very much. Thank you for your attention. Wish you have a wonderful conference.